growing up as a kid in New York, I always enjoyed going into the city and seeing the Hayden Planetarium. So I was really pleased when I was asked to be part of a group of astronomers who were asked to help them redesign and think about how to create the new stunning planetarium that's in New York today. When we were gathered in this committee, we were asked by the designer to summarize all of astronomy in a single line. At first, this seemed incredibly daunting, to take all of the science we've learned from the ancient Babylonians, the Egyptians, Galileo, Newton, Einstein, the most recent results from the Hubble Space Telescope, and reduce it all to a single sentence. We sat there for 3 hours, struggled to summarize all the things that we've done. I think as any scientist could talk for hours about the importance of their particular contribution. We sat down and we finally came up with a single sentence, the theme of today's lecture, which for me is the most important thing that people should know about astronomy. And that's the idea that the universe is big. And this is the first of a series of lectures in our class. The class will consist of really 3 main parts. We'll begin by exploring our own solar system. At the end of that section, we'll have an assignment where you'll write a paper or make a presentation about one of the ideas for building new satellites to explore our solar system. The second section will be focused on stars and the new planets that we're discovering around these stars. That will end with an assignment where you'll write a paper or develop a presentation on some of the new missions we're hoping to do to discover planets around nearby stars. And then the final section will return to the Earth and look at the history of life on the Earth and look at how life evolved, how evolution works, and then apply those ideas to extrasolar planets and think about how life might evolve elsewhere. The final assignment, I think, will be the most exciting and the most challenging. You will create your own solar system, imagine how life evolves on that solar system, take some of the lessons we've learned from looking at Mars and Europa and Earth and apply it to your new planetary system. I want to begin this course with 2 introductory lectures. Today's lecture where we'll talk about the universe, and tomorrow's lecture where we'll talk about the origin of life, what is life, and how we might detect it. Today's lecture and many of the lectures will consist of several parts. You'll have a segment of about 15 to 20 minutes. That will be followed by 1 or 2 short questions. You'll answer those questions, then return to the lecture. There'll be another segment of about 15 to 20 minutes, another set of questions, and then the final part of the lecture. In this lecture and in some others, I'll try to embed some videos that I'd like you to look at either during the lecture or at the end of the lecture. So let me now begin here and talk about our place in the universe. Begin first with our own solar system, then turn to our galaxy, and finally look at our place in the universe as a whole. So we're going to start with the Earth. Here we are on Earth. We're right here in New Jersey. You're spread out somewhere else on this planet. And let's just begin by looking up some basic facts about the Earth. What I'd like you to do is actually pause the lecture for a moment, go into Google and type in the following things: Earth mass, and that what should come up is the mass of the Earth; Earth radius, what should come up is the radius of the Earth; and how far is the Earth from the Sun. One of the wonderful things about having the web today is you can look up all the basic astronomical numbers that you might need for any of the problems that we'll look at in this class. So later on, we'll be looking at things like how far is Mars from the Sun. If you want to know that, type that question into Google. What will come up is that distance. Also, all the basic constants of nature, the speed of light, the strength of gravity, all those numbers will come up immediately if you type in gravitational constant or light speed on the web. This is extremely convenient. In the old days, you would have a textbook for your introductory astronomy class that would have a list of all those numbers. Now, they're immediately available to all of you, and I will not be providing them in the questions I'm asking, and if you want those numbers, you should look them up. So I hope you've looked up those numbers, and I want to start with this number: how far is the sun from the Earth? That distance is what we call an astronomical unit. It's about 150 million kilometers. And of course, that's about roughly the distance the Earth travels, or 2 pi times that distance is the distance the Earth travels as it orbits around the sun. That will be our measure, our ruler, for looking at the distance to stars, for when we talk about other solar systems and we compare how far their planets are from the star. We will often want to talk about the distance that a planet is from its star in astronomical units. And if a planet's 1 astronomical unit away from its star, its distance is the same as the Earth from our sun. Some of the planets we discover by direct imaging we'll find are 10 or 20 astronomical units away from their star, so they're much further out. They'll be colder planets, much like Saturn or Uranus. The Kepler telescope has been exploring the inner regions of solar systems, and it has discovered many planets at half an astronomical unit, a third an astronomical unit, even a tenth of an astronomical unit, much closer to the star. Now let's turn to planets. I hope that tonight you all go out and look for planets. And let me teach you the first thing you need to know to be an expert astronomer. Stars twinkle and planets don't. So when you look at the night sky, if you see something that's bright and flashing and moving, that's an airplane. If you see something that's twinkling, it's a star. The brightest twinkling star you'll see in this time of year is probably Sirius, which is the brightest star in the sky. And depending on when you look at night, you'll see different planets that are up. Venus and Mercury is hard to see, but Venus is quite bright. Venus is always close to the sun, so depending on the time of year, you will either see Venus soon after sunset or right before sunrise. Jupiter is the other very bright star, well, bright planet, and it also, you can look for, it's not twinkling, and it's often seen directly overhead. If you want to see what's up in tonight's sky, let me just recommend 2 websites that I've listed here, and I would encourage you to go look at these websites tonight. Go out, and if it's a dark, clear night, see what you can see. See if you can find some of the planets yourself. If you have binoculars, I encourage you to look at Jupiter. And if you're lucky, you'll see not just Jupiter, but its 4 most massive moons. These moons were first discovered by Galileo when he turned his telescope to the night sky. When the ancients stared up at the night sky, they noticed that some stars stayed fixed and some, what they thought were stars, moved. They called these ones that moved wanderers, and those wanderers were planets. And planets, their positions across the sky change. And this change and this motion takes place because while the stars are far away, the planets are close. So the relative positions of the Earth and the other planets move as they orbit around the sun. And this is why Mars or Jupiter or Saturn appear at different positions in the sky as they move around their orbits throughout the year. So let me encourage you, and these are questions that I want you to go off and do after lecture because it requires getting away from your computer, stepping outside and looking at the night sky, seeing if you find any planets, and go stare at the moon. See what the phase of the moon is, and watch over the next month how the moon's phase changes. If you have access to binoculars or a small telescope, point it at the moon. See its craters, and see this remarkable fact that so excited Galileo that the nearby planets were not perfect. The moon wasn't a perfect surface, but it's this cratered structure, and as we now understand it, those craters reflect the whole history of the formation and evolution of the solar system. So here's our solar system, with the Sun in the center, followed by Mercury, Venus, Earth, and Mars. These are what we call the inner planets. And you'll notice they fill this tiny region. The distance from the Sun to the Earth, our astronomical unit, is much smaller than the distance from the Sun to Neptune. So as we move out, we then have Jupiter, Saturn, Uranus, and Neptune. And the inner solar system is a much smaller region than the outer solar system. This is actually an old figure, and it includes Pluto as one of the planets of the solar system. As I'll argue later, Pluto really ought to be grouped in with the other dwarf planets. Here again is the outer solar system, Jupiter, Saturn, Uranus, and Neptune. And you can see Pluto is different from the others. It's on a very different kind of orbit, much like the other dwarf planets that have been discovered in the past decade. Here's one of them, Eris, whose properties are much like Pluto. And Eris is but one of the many objects in what we call this Kuiper belt, built up of remnants of the formation of the early solar system. This is another way of displaying a map of the solar system, but here we're using what we call a logarithmic scale. So as we move out here, we're looking at factors of 10. So the distance from the Sun to the Earth is 1 astronomical unit. To Saturn is 10 astronomical units. And we're using scientific notation here, where 10 is written as 10 to the 1 power. The distance out to what we call the terminator, the boundary between the material in the solar system and the interstellar material, is about at 100 AU. This year, a remarkable event took place in our exploration of the universe. The Voyager spacecraft crossed the terminator, crossed the boundary between our solar system and the material outside. Now, while it's crossed this point, it still has a very long way to go to get to the nearest star. The nearest star is not 1,000 AU or 10 to the 4 AU. The nearest star, Alpha Centauri, is out here at more than 100,000 astronomical units from the Sun. So you can see the distance to the nearest star is much, much further than the distance to the planets, right? That's a factor of about 10,000. And Alpha Centauri is the nearest star. The typical star we see in the night sky is 1 million or often 10 million astronomical units away. Now I'd like to turn to the first problem. And the goal of these problems are twofold. One, it's a chance to improve your quantitative reasoning skills. But also I think it's important to sit down and think about some of the concepts that we're talking about in the class, make some rough estimates, and get a feel for some of the numbers we're talking about. In astronomy, we deal with really big numbers. And I think one of the ways to make sense of them is to start thinking them through. What we'll do with these questions is the lecture will end. You will leave the lecture, do the question online, answer it, and then return to the lecture. The first question we'll do is we'll look at how long it takes to travel from the Earth to Mars at their distance of closest approach in a rocket. And to make this problem easier, we're going to keep Mars and Earth fixed. So the way to estimate this is to go look up the Earth's distance from the sun, look up Mars's difference from the sun, take the difference between the two, divide by our velocity, and figure out, will our astronauts take 10 days to get to Mars, 100 days, or 1,000 days? So I'm going to stop here. Why don't you think about that, answer the question, we'll come back and discuss it, and then turn to the next part of the lecture. Welcome back. You should have found on that problem that it'll take roughly 100 days to travel from Earth to Mars if neither planet moved. The real situation's a bit more complicated. The Earth moves on its orbit around the sun. Mars moves on its orbit around the sun. So if we are to travel from Earth to Mars, we'll have to go on one of these transfer orbits. Because the path is somewhat longer than moving on a straight line, it'll take roughly 200 days to travel from Earth to Mars. This is much longer than the roughly 4 days it takes to go, say, to the moon. And because of this longer travel time, this mission is about at the edge of what we can do technologically. That said, like many people interested in space exploration, I think that Mars is the next obvious destination for human exploration. As we'll see later in the course, there's a tremendous amount that we'd like to learn about Mars. We've gained a great deal of knowledge from our rovers and orbiters that have gone to Mars, but it'd be very exciting to be able to send humans. But this 200-day journey is going to be very challenging. We're going to have to worry about a very hostile space environment, and this will be a great challenge, but one that I hope we rise to within our lifetimes.